Hello, can I share my screen? Hello, can you hear me?
We can, Vipin.
Oh, wonderful, thank you. Welcome to the second workshop on knowledge-guided machine learning. My name is Vipin Kumar. I'm a professor at the University of Minnesota. This is the second workshop in the series, which builds on the success of the workshop we had last year. This year, we have about 1,300 attendees registered from over 30 plus countries. And just like the last year's event, all the talks and slides and videos will be posted on the workshop website after the event, subject to the permission by presenters, and most of them have been kind enough to give that presentation, the permission. As last year, we will have the question and answers via Slido, and the information about how to access Slido and any other logistics information are available on the workshop logistics page. And I would urge you to visit that web page and click on the logistics links to learn about any other details that you need to learn about accessing issues. A new feature this year is a poster session that we'll be holding via GatherTown each day between 12:30 and 1:30, approximately 12:30 and 1:30. And it's basically, since we're doing it for the first time, we'll of course look for how the session goes and learn from the feedback that we receive and hopefully do it better next year. This workshop is supported by the NSF Harnessing the Data Revolution program, specifically two different projects that span 10 universities on knowledge-guided machine learning, a framework for accelerating scientific discovery, and another project, physics-based machine learning for subseasonal climate forecasting, that's anchored at University of Illinois. So as sort of you all know, we are in the age of data revolution, which sort of is enabled by tremendous progress we have seen in the technologies in big data, ability to collect lots of data in many, many different disciplines, developments in high-performance computing over the last 4 decades, as well as tremendous progress that has been made in machine learning, particularly in the last few decades, and even more so in the last 10 years in the area of deep learning. And all of these combined have revolutionized the way, all aspects of our life. And increasingly, data science methods are being looked at as alternatives to traditional methods that people have used in the scientific disciplines. And I must add that the use of statistical and data science methods is not new in scientific disciplines, and the traditions go back in disciplines like hydrology and biology in terms of bioinformatics, many, many decades. But this has sort of picked up a lot more attention in recent years. And then you see the big data being referred to on the cover pages of Nature and Science. But even here, this attention has been sort of there for quite some time. This Nature cover that you're seeing here is from 2008, about 13 years ago. What has happened is that especially in the last 5 years, over the last 5 years, people have begun to see the tremendous utility some of the latest advances in machine learning bring to the scientific disciplines. And as a result, you see this harnessing the data revolution being one of the big 10 ideas from NSF as a special program. So basically, there's a tremendous interest in leveraging the power of the latest advances in data science and machine learning in the scientific disciplines. Now, while you see a lot of such developments, a lot of such applications in scientific disciplines, but it has also been accompanied by skepticism, sometimes a hesitancy to adopt machine learning for mission critical applications as a first class replacement for the traditional methods. And these hesitations is due to a number of issues that one can expect with black box machine learning, and in many cases, which have led to even to spectacular failure, like, for example, Google flu trial. Now, and I'm going to list some of these here, and one of them is that the machine learning algorithms have done obtained tremendous success in many areas, but the same state-of-the-art ML algorithms also require a lot of data, and scientific disciplines, even though they have a lot of data, but the data that can be used as trained for training with the labels can be very limited in many cases. Because these methods are looking for statistical relationship, of course, very sophisticated statistical relations, they can often generate results that are physically inconsistent in the sense that they won't sort of make sense to a scientist in the sense of being physically correct. And that sort of increases the skepticism in their power. And the biggest, of course, the concern with many of these data sets is that they are able to find patterns in the data that you bring for training, but they're unable to generalize to scenarios that are unseen and very different than the one that we use for training. So in the sense of the ability to extrapolate beyond seen scenarios can be very limited. And that's what I meant by failures in reality. That is, you build a model, you test it, you think you're getting good cross-validation accuracy, and you're ready to deploy it. And then you get disappointments. And again, even if you were able to get good predictive performance using these methods, predictive modeling, even high performance predictive modeling without clear mechanistic understanding does not advance science. So that's another reason for skepticism and adoption of these methods in practice. And one of the perhaps underlying theme that runs all of this is that many decisions that involve physical and environmental systems impact the well-being of the population and the broader ecosystem. And as a result, the decisions that you make using these methodologies have consequences for people and for ecosystem. For example, missing a flood warning, as we have seen many cases in just the last month in Germany, in India, and China, very serious floods can have far more serious consequences than recommendation of a wrong product that sort of runs over internet industry and of course, many other things. So as a result, there is a increasing, interest in new kinds of machine learning algorithms, and let's call them scientific knowledge guided data science models that are guided by scientific knowledge that build on the state-of-the-art data science machinery while taking full advantage of the scientific domain theories. And of course, these methods are different than pure black box data science models that work really well when you have lots of data without having much access to the scientific knowledge. And a poster child for that application, I would sort of say, is the language translation. Today's just by using billions and billions of pieces of text that are available on the internet in different languages, it's possible to create pretty good quality translation to the extent that each one of us, when we travel anywhere, we can use an app on our smartphone and point it to any language text and get a reasonable translation. And these translation methods use very minimal use of the latest and greatest linguistic theories. And these methods are also sort of on the other extreme, very different from the pure scientific models that sort of use the first principle methods to build a mechanistic model and then use them to make predictions while making limited use of data for perhaps calibrating some parameters. But as a necessity, these models are incomplete and approximate representation of reality, and they don't do very well. And the hope is that these new generation of methods that sit right in the middle are going to be able to cover for the weaknesses of both of these types of methods. And underlying philosophy in this rich area of scientific knowledge-guided data science models is that the data in scientific applications is the recognition that the data in scientific applications are governed by laws of nature, such as conservation of mass and energy and momentum, and involve physical and biological regulatory mechanisms. Now, this general direction of bringing science and machine learning together sort of is a relatively new phenomenon in the sense that even though the use of machine learning has been in scientific disciplines is very goes many decades, even longer. But being able to sort of explicitly try to integrate a scientific knowledge deeply into machine learning models beyond the traditional ways of doing feature extraction or feature selection is a somewhat recent phenomena. In our own work, we sort of stumbled on it while we are sort of working on this NSF expedition project on understanding climate change using data science methods. And we noticed that unless we modify these algorithms to incorporate scientific information, it's very hard to make them do good work. But the progress in this work has been tremendously expedited in the last 4 years, especially since 2017. And there's a tremendous interest in this area, and the work is progressing from multiple groups and independently, and then of course they're coming together. In our own work, we sort of published this paper in 2017, and around the same time, a series of very influential papers were published by a group of Professor George Kaniadakis, who will be giving a keynote talk in the closing session on Wednesday. Now, these methods, as I said, are being used in literally every single discipline. The methods that I'm talking about, knowledge-guided machine learning, oftentimes they're also called physics-guided methods or physics-informed methods or theory-guided methods. There are different names. And very recently, we did a survey of work in this area, and there are, it turns out there are about at least 300 papers published on this topic in just the last few years. There are programs that are coming out of agencies like NSF and DARPA and DOE, and you're also going to hear a talk by the Chief of Data Science at USGS, Jordan Reed, first talk right after the break, who's going to talk about how the Kgml, the knowledge-guided machine learning, is impacting the USGS's water mission. You also see a whole bunch of conferences and workshops on the topic. In last year alone, in 2020, there were 6 such events, one of them being the 2020 Kgml workshop, which was attended by, it was the first workshop on the topic. It was attended by over 1,000 people from 30 different countries. So this sort of shows the tremendous interest the topic has around the world. This workshop specifically focuses on Kgml, 4 Kgml applications, so weather and climate, aquatic sciences, hydrology, and transition biology, because these were the applications that are sort of part of the HDR project. But the concept, the machine learning concept of Kgml, the basic concept of Kgml apply across many different disciplines. And you're going to hear talks about that are focused on, of course, on these 4 sessions, 4 topics in the 4 sessions, but many other topics would be covered as well, especially in the machine learning 1 session, which you are in, and as well in the closing session. And just to outline, for example, there's a talk on agronomy, being able to use the Kgml models to more effectively model the carbon cycling in the agricultural processes. That'll be the last talk in the morning session today. Now, these different applications, these 4 applications, as well as many other, share a range of challenges among them. And of course, the Kgml approach brings lots of opportunities to address those challenges. And let me just very quickly go over these challenges. One challenge that's common to literally quite a few of the applications is the sparsity of training data. I mentioned that earlier, and it's the fact is that even though we have tremendous amount of data, for example, we have tremendous amount of climate and weather data, but the part of the data that can be used for training ML model can be very limited. For example, we have global data set for climate going back literally decades and farther reanalysis data sets. But if you use them as training sets for prediction, you're talking about 40 to 50 years. That means 40 to 50 samples for making predictions that are really high quality for predictions. And you can go back to, of course, older years by looking at somewhat less accurate data set, but still the amount of data that's available in the terms that machine learning can use for training can be very, very limited. That's one part, and that's this theme runs across many applications, and you will hear it again and again. The second aspect that is also common to literally every one of these applications is this heterogeneity in space and time, the relationships between the features and the target variable that you try to learn in machine learning can be learned as long as you have the right sort of training set. Now, but this relationship can change in both space and time. They can change over time in the sense that these phenomena may not be stationary, and they can change in space in the sense that different regions, the hydrological model that works in the Midwest may not work in Europe, may not work in China, or even different part of the US. So basically, each region, each location has a different characteristics, and as a result, the relationship change, and being able to learn generalizable relationship is extremely important. Otherwise, the methods would overtrain and would give you a false sense of security. The other thing that is very different between the way typically the model build predictive models in machine learning versus scientific applications is that we're talking about processes that need to be modeled that are evolving and interacting at different spatial and temporal scale. So temperature could be changing rapidly. The wind flow could be changing even more rapidly, but the soil moisture changes much, much more slowly. And all of these things interact together to have impact on whether you're going to get a flood someplace or whether the forests are going to get turned on for fire depending on the heat, the high heat temperature, because the soil, which changes very slowly, can of course have impact as well. So all of these issues of sparsity, heterogeneity, and ability, the need to model complex processes that runs across literally vast majority of the applications, and you will hear about these throughout this workshop in many of the talks you will hear. And the last challenge, of course, is very important and very critical, and again, it's because of the mission critical natures of these applications, and there's a need for transparency. The high prediction accuracy is not enough for us to be convinced that they should be used. You have to really understand how they work. And there's a tremendous progress, again, in addressing all of these challenges, because you could modify the traditional paradigm of machine learning by bringing in loss functions in the learning framework that are guided by scientific knowledge, by being able to initialize these machine learning models using the knowledge that you have about these interesting physical processes, the conservation laws, and even mechanistic models that may be imperfect, but may be still able to initialize these models. And design of specific architectures that incorporate the structure of the physical application that you're trying to address. And in many cases, people would combine build hybrids of these physical models and machine learning models. And as you will sort of attend these 36 talks spread over 6 different sessions in this workshop, you will notice all of these different methods, examples of all of these different methods, literally in every one of the talks that you'll be seeing. The another huge commonality among all of these scientific applications, many of the scientific applications, but not all, is that there's a notion that you're trying to build a model of a physical system. This physical system has certain inputs, let's call them xt. These are the dynamic inputs at time t. There are outputs that you're trying to predict, let's call them y at again time t. System has a static characteristics. You could call them latent parameters that govern the relationship between xt and yt. And f is the model that you're trying to build to be able to predict y given x. For example, if you were doing the modeling of lake temperature, the weather drivers like the amount of sunlight, air temperature, wind speed would be xt. You may be interested in predicting the temperature of the lake at different depth. That's the yt. Y has both the spatial and temporal dimension. And the state of the lake could be parameters like clarity of the water or salinity and so forth. And again, this model that you're trying to build could be purely a physical model, which is of course what typically people do. For example, in the lake temperature modeling, they have the generalized lake model, GLM, whereas or you could build a pure data science model, which would just look at the samples of observations from xt and yt and try to build a relationship. And of course, the goal of this community of working on knowledge-guided machine learning is to build these models that are informed both by the physical laws as well as the latest advances in machine learning that allow us to build very sophisticated relationships. Okay? And there are generic objectives that people pursue in this area, and some of them, and I'm going to list 4 of them here at a very high level. And one of them is being able to create this forward model that is given xt. My goal is to be able to build a emulation, build this function f that can translate x to yt, and of course for systems with different sort of parameters. And the idea is that if the f was being built using the traditional scientific approaches, it would be necessarily incomplete or approximate, and you want to leverage information in those scientific models along with the observations to be able to build a model that's more accurate and perhaps more robust and more generalizable. There are also related sort of models which could be called as emulators or surrogate models, where you happen to have a physical model that you trust is reasonably good for you, but it's very expensive to run computationally at the desired spatial and temporal scales, in which case you're trying to build a machine learning emulator for it that is faster. So in the second case, you're not short of the labels, because we can generate the labels from the computationally expensive model. So the objectives are similar, but the settings are a bit different, but they share many aspects. And these methods are going to be subject of vast majority of the talks that you will see in this workshop. There can also be a situation where you have this weather drivers, or you have the inputs and you have the outputs, but you're trying to learn the intrinsic physical parameters of the system. So also goes by the name of inverse modeling. It's a very hard problem, and there's tremendous progress that's being made in this area. And there'll be 2 talks in the hydrology session tomorrow morning, and there could be others in the meeting too, but at least 2 talks that specifically deal with this aspect of inverse modeling. There's a tremendous interest, as I said, in making these models transparent and also extract knowledge out of these machine learning approaches. So here the idea is that I'm trying to figure out something about this the box F, the model, and there's a tremendous work in this area on discovering governing equations. One of the founders of the field, one of the person who has done founding work, Nathan Kutz, is going to be giving a talk in the closing session on the workshop on Wednesday. You will hear about reduced order modeling, where you have the physical, you may have physical function, which is highly complex, but you're trying to figure out a reduced representation. And then a third line of reasoning in which you're trying to figure out, given a ML model or a Kgml model, you're trying to figure out techniques to be able to understand exactly why it works. And there are almost half a dozen talks on this topic. There are several of them that are going to be focused on this issue in the afternoon session on climate and weather, and of course throughout the workshop. And the last one is about dealing with the uncertainty, and of course the traditional notion of uncertainty deal with how does the model predict, what is the uncertainty in the prediction of the target parameter like yt in forward modeling, or perhaps s in case of inverse modeling. But there is another very interesting direction that's being pursued by this community, and it's called the forecast of opportunity, in which you're trying to identify the states of the system that leads to more predictability than the others. And the third talk in the session today by Levi Barnes is focusing on this aspect. So again, to conclude, I just want to sort of leave with a note that the early efforts to merge scientific knowledge into machine learning have led to promising results. You will hear many interesting examples of it today. Much of this work has been proceeding in isolated domains directed towards specific application, but there's much to be learned from the cross-pollination of ideas among these diverse research communities. And that's precisely the idea of a workshop like this, and hope that we will all be wiser and smarter after hearing all of these wonderful talks. And there are increasing expectations that this paradigm would be able to help us address some of the biggest challenges that are facing the humanity in climate health and security. And for the climate change, the 6th assessment report of the ICPP just came out just a few hours ago. And there are a number of people who will talk about that, especially Arup Ganguly, who will talk about those issues in this closing talk, one of the closing talks on Wednesday afternoon. And lastly, but not the least, the Kgml approach is not, our hope is that Kgml approach is not just meant to advance scientific disciplines, which of course is an extremely important discipline at Denver, but it's also expected to spur new advances in machine learning because of the challenges that we bring in from the scientific community. Now with that, I am going to now introduce the chairs of this session, Professor Arindam Banerjee and M.A. Ebert-Hupaf, and I'm going to have them take over and introduce the next speakers in the meeting. Thank you. I'm going to stop sharing.
Thank you, Vipin. I think our understanding is that we want Libby to go next. So I'm going to introduce Libby so we can move on with the program. So I'm actually excited to introduce our colleague, Dr. Elizabeth Burns. Libby is an associate professor at Colorado State University. Her research largely focuses on climate variability and change and data analysis tools to understand it. So on a personal note, her work is actually an excellent example of combining deep domain knowledge and expertise with ideas from machine learning. And we'll get to see some of that, which is really the theme of the workshop. And she has taken on several leadership roles in the community. She leads the new US Climate Working Group, the Emerging Data Science Tools for Climate Variability and Productivity. She serves on the CSM Science Steering Committee, among many others. So please join me in welcoming Libby.
Thank you very much for the invitation to speak. And can you hear me? Thumbs up, somebody?
We can.
Thank you very much, and hopefully see my screen. All right, so as Arindam just announced or introduced me, I am really an atmospheric scientist. I study climate variability and change, but I've always had a love for data analysis, and obviously machine learning falls into that category. So today I want to talk to you about some work I've been doing with my colleague, Professor Randall Barnes, thinking about how we can really merge how we think as geoscientists about our data, and some new work we've done trying to create new machine learning methods to really help us advance this way of thinking. And specifically, I'm going to focus on the concept of forecasts of opportunity, which Vipin mentioned, and I'll go over briefly again. So today I'm going to tell you specifically about what we call controlled abstention networks, or CANs. All right. So what's the motivation here? So the Earth system is exceedingly complicated, and it's often, at least in my world, in the atmosphere, chaotic in nature. So really making predictions is incredibly challenging. Just think about looking at your phone and figuring out what the weather is going to be, next weekend if you want to have a picnic. This is a hard problem that we've been working on as a society, trying to predict the weather for a very, very long time. So in bold here, right, we cannot expect, at least in my world, I cannot expect to ever make perfect predictions all of the time. The Earth system is just too complicated. And so instead, in many ways, when we think about machine learning, we think of, or when we apply machine learning methods, we think about making perfect predictions is really what the goal is. And here I want to challenge that concept by saying, in my case, we don't think we're going to ever make perfect predictions. So let's try to focus on those predictions that we make when we can. So specifically, the abstention loss, and here we mean abstention as in saying, I don't know, or abstaining, works by incorporating uncertainty into the network's prediction. And it allows the network to identify the more confident samples and abstain, say, I don't know, on the less confident samples. Now, there are many different ways that we've been incorporating uncertainty into machine learning training for a very long time. So I don't mean to say that we are the first in any way to do this, but we're trying to put a slightly different tweak on it in the way we think about our geoscience problems. So specifically, the abstention loss is applied during the training process rather than after the fact to preferentially learn from the more confident samples. In the case of atmospheric science, you could think of it as this as preferentially learn which forecasts we might actually have a better chance of getting right than others. Okay, so the general idea here, first I want to point out the upper left-hand corner of my slide. This work is very, very heavily influenced by a dissertation that just came out in 2020 by Dr. Sunil Tulasidasan. There we go. And I've put those links here, so please take a look at that work. And I will be sharing these slides. All right, so here's the idea. First, we want to estimate the uncertainty of each prediction during training. We're going to be focusing both on classification, which is well known in the machine learning community, but also regression, which is maybe less appreciated. But in climate science or in atmospheric science, regression is really mostly what we do. So it's very important that the tools we're developing can be applied to regression problems as well. So we're going to estimate the uncertainty for each prediction, and I will talk about this more later. And then we're going to implement a loss function that learns to identify more confident predictions and learn them better during training. For classification, we have introduced a loss function called the not wrong loss, but today I'm really going to be focused on the regression application since this is more new and relevant to the geoscience community. So we're going to modify a negative log likelihood, and I'll talk more about that. And then finally, we're going to compare this new abstention loss method to a more baseline method that we would maybe use until this prior to this method. And what we're going to show is that the baseline methods, they perform very well. However, this abstention method appears to outperform the baseline for a variety of tasks that we've identified in geoscience. All right, so step one, adding uncertainty to regression tasks. To many people, I think in the computer science community, this is probably trivial, or that you have many ways of doing this. But from the geoscience community, and I know many of our viewers are from the domain site, the specific domains. There we go. This is not at all obvious how one might do this. Okay, so how might we do this? So let's say we have some data that looks like this. So X is on the X-axis and some output Y. We want a neural network that makes a prediction and estimates the uncertainty of this data. So what we really would like is we would like it to predict some sort of, say, distribution of its prediction. In this case, imagine that the true label here is Y, shown in the pink line, but what we want the network to do is predict this blue curve, predict the distribution. In this case, it's a Gaussian. And in fact, we can do this with a neural network. We can predict, in this case, the median and the 80% confidence bounds quite well using a very simple method that I want to talk about here. And we are writing up a overview of this method for domain scientists that want to implement uncertainty in their regression problems. Okay, so what is it we want to do to set up this abstention network? We want a neural network that predicts, that makes a prediction and estimates the uncertainty or predicts a probability distribution. And we're going to use the maximum likelihood estimation or the negative log likelihood. So typically when we think of regression problems, we predict Y. And instead what we're going to do is we're going to output two values instead, mu and sigma. These additional outputs now represent the parameters of a local distribution. In this case, let's assume it's a Gaussian. And so the mean predicts the mean of the Gaussian, and sigma is that standard deviation. So we can use the negative log likelihood where pi is a value that is obtained from the normal distribution that's predicted by the network. That is, you can imagine the network predicting, say, one of these blue curves, which is a normal distribution with the mean mu and standard deviation of sigma. And once that prediction is made, we can estimate, or we can compute this p sub I value by drawing a pink line here, y sub I of the true value. And that p sub I is merely this probability density function at that particular value. So on the left-hand side is a case where the network is overly confident. The standard deviation is too narrow and it misses, that true Y. In the middle, it's underconfident. The standard deviation is far too wide. And once again, this p sub I value is far too low. And on the right-hand side, you can imagine this is the type of prediction we'd like our network to make when it predicts the probability density function. It looks pretty good compared to the true Y value. All right, I'm giving all of this background because this is really what leads to our baseline approach that we're going to be comparing our abstention networks to. Specifically, imagine we put a sample into our neural network and it outputs some predicted Gaussian, mu, and sigma. If we put many samples through our network, we're going to predict many different distributions, say these four here, for 4 different samples. In this case, by looking at that spread, you can say that the blue curve, the network is very certain of its prediction, whereas in the purple curve, the network is far less certain of its prediction, given that larger standard deviation. So this baseline approach is to train the model and then ultimately sort the results by sigma, or how certain the model is by that spread in its PDF, predicted PDF. And then the concept of our forecast of opportunity is to keep only the X% most certain distributions. So this approach has already been used in the climate community to try to identify more predictable states of the climate systems than others. And we show that, and indeed, the network is more confident in cases where the weather evolves in a more predictable fashion. And so it's really important to point out that this baseline method is already a very powerful tool for identifying forecasts of opportunity in data, especially and specifically for regression tasks as opposed to classification. Okay, now what about abstention during training? I said the whole point of this was to abstain, for the network to be able to say, I don't know on certain samples. So I'm not going to go into all the details here, but specifically, our abstention loss is very similar for both classification and regression. And the way to think about it is it's a regression loss, that's a modified log loss, as I already showed, but it's weighted by a prediction weight that is determined by this predicted uncertainty sigma. So if you will, our loss function for a particular sample xi can be written in the following way, where you see here that log p appearing again, but it's weighted by this qi term. That is a prediction weight that comes from some scaling of this uncertainty in sigma. Now, if that's the only term that you have, the network would quickly learn that it should say, I don't know on everything, and it will minimize the loss. So we also have a second term here that controls the amount of abstention. And this alpha allows us to either choose what that abstention is. That is, we want the network to predict, say, only throw out 20% of the samples or predict 80%. Or we can also train the network to predict the best abstention fraction. That is to actually predict the amount that is preferential to abstain on and to keep. All right, so this is where we sort of started from, again, my simple geoscience background. I thought, well, what if I had a data set that looked something like this, where 80% of the samples were in some cloud over here on the right-hand side of the image, and only 20% of the data fell along a clean line. Now, as a scientist, I would look at this and I would say, oh, well, a bunch of the data is really noisy, but there's this really nice behavior for 20% of the data. And so I should draw a line through that data alone. And this is this concept of forecast of opportunity again, that many of our samples are just relatively unpredictable, but hidden inside of all that climate noise is a signal that might be predictable for some samples. So when we use the abstention network for regression to predict, so to feed it all this data and learn the relationships, the abstention network learns to only predict 20% of the samples on average. And indeed, it's the 20% that lie along that nice line. And it throws out the samples that fall above about x equals 2 because it's noisy. And it learns that that noise it should abstain on. Okay, so another way to say this, how does this compare to our baseline method where we retain only the say 20% most confident samples? And what I show here is coverage, or the percent of the samples actually predicted that is not abstained, are on the x-axis, and the mean absolute error of those predicted samples is on the y-axis. The solid purple line here is our baseline approach for many different abstention fractions or coverages. And the big point is, first of all, even with this baseline approach, as we throw out fewer or more and more of the samples, that is, as we retain the most confident samples, the mean absolute error goes down, which makes sense. The network does a better and better job. However, the more important part here is that if we look at what the abstention network does, that's shown in these orange dots here, it learned to only retain 20% of the data, or abstain on 80%, and it outperforms the baseline method in its error. Now, this is a pretty silly example. I just did XY data. As a scientist, we could look at this and draw the line. We didn't need machine learning to help us do this. So let's go on to a more complex example. Specifically, I'm going to use a data set that was developed as part of this, the Kgml project by Dr. Antonius Mamalakis, who is advised by Dr. Ebert Uphoff and myself here at CSU. And so what he's done is he's created a synthetic climate data set where the samples or the inputs are maps of synthetic sea surface temperatures that have nice behavior the way and correlation, spatial correlations the way sea surface temperatures actually do. And their labels or their Y values are created as a nonlinear function f that maps each of these x's onto the scalar y. You can think of it as some sort of nonlinear weighted sum of the sea surface temperatures over the globe. Now, the behavior of f is not important other than for you to know that we know what f is because Antonius designed it himself. So we know the right answer. We know how this data was created. So what we're going to do is we're going to task the network to predict the value y for each input map of these sea surface temperature maps. But instead of just predicting y, we're actually going to have it once again predict mu and sigma, so the parameters of a Gaussian distribution. Now this alone doesn't have anything to do with abstention because we know there is a nice relationship between every map and its output. However, what we're going to do is we're going to go in and we're going to actually mess with the data a little bit, the way sort of chaos, if you will, in the climate system messes with our data. That is what we're going to do is we're going to go in and we're going to look over the El Nino region. That is the tropical Eastern Pacific Ocean. And in samples where that region has a value on average greater than 0.5, we're going to leave those samples untouched. Otherwise, we are going to shuffle all of the data. That is, we're going to break the relationship between a map and its output. The idea here is, once again, this forecast of opportunity, that only samples with strong El Nino signals will have a learnable relationship with their labels. All other samples have been completely shuffled. Now, we can do this both with our baseline approach and with our abstention network for regression. And once again, this is what we get. So the coverage, or how the percentage of samples that the network chooses to make a prediction on versus the mean absolute error. The purple and the purple shading denote the baseline approach over many, many different networks. And the colored dots are the abstention network for various abstention fractions that we have set. And the point here is, first of all, the abstention network outperforms the baseline approach on average, but it does a much, much better job than the baseline, that is a much lower error, when the coverage is right around the right percentage of how many samples in the original data set were worth predicting. That is about 20 to 30%. So this shows how this abstention network is helping us identify these forecasts of opportunity within our data set. Now, I've just shown one particular example how we can shuffle the labels, but there are other ways of adding noise to the data. For example, specific labels can be corrupted, so structured noise. I've shown we can have arbitrary label noise. Another example is corrupted inputs, where we can use the abstention network as a data cleaner. For example, imagine our sea surface temperature map originally looked like this, A on the left, but it was corrupted. Let's say certain pixels just got a value of -4 or -3, as shown in blue. The abstention network can actually learn to ignore these samples and thus learn the true relationships better on the non-corrupted samples. And so again, showing that these dots are out for the abstention network have a lower error than a baseline approach. So if you're interested, we have our papers on these controlled abstention networks for both classification and regression up on arXiv, and they are both currently under review in James, which is an atmospheric science journal. The code is also up on GitHub, both, again, the classification and regression code, if you are interested in playing with it. Okay, so some take-home ideas for the domain scientists. Predicting the local parameters of a probability distribution is a simple way to add uncertainty for regression tasks, which is something that many of us deal with every day. And the abstention loss for regression classification really allows the network to identify these opportunities for skillful prediction. I framed it in terms of climate and atmospheric science applications, but I want to be clear that it doesn't have to be a forecasting weather problem. Really, any data set where you think that there are relationships hidden amongst a lot of noise, or put another way, where you think only specific samples have an opportunity for skillful prediction, the abstention approach may be useful for you. And then finally, I didn't hammer too hard about this, but implementation of abstention loss is really straightforward and just involves changing the number of outputs that you're predicting and the loss function. What that means is it can be applied to a wide variety of network architectures, not just in this, as we did here, say feed-forward networks. And with that, I will point out that my slides will be shared and I have some citations here, but I can take any questions that may have come up. Thank you.
Thanks, Libby. That was an exciting talk. There are some questions. So I'm going to pass on some of these questions to you. I have a couple of questions myself. Maybe I'll start with the ones that are on Slido. So one question says, how do you handle the case where the model is wrong with great confidence?
Yeah, so I mean, I think the goal is to train a model that is not wrong with great confidence, right? That's the ultimate goal. In the examples I've shown here, we are able to quantify and show, since we know the right answer, we're able to show that the model confidence scales very well with how often, if you will, it's wrong or it's that probability distribution. I think the bigger concern is that in data where you don't know the right answer, how do you know that that's actually occurring? And I think there are some methods out there. Here we use negative log loss, but there are other loss functions that can help ensure that the confidence scales with, say, how often it's wrong or how often it's right. But I don't think, unfortunately, that I have an easy answer for that. I think that's one of the holy grails of predicting, uncertainty.
Yeah, so that actually your response reminds me of this notion of calibrated forecast, where which people have studied for a while. Okay, so that's the direction this kind of research can go and benefit from.
Yes.
So next question: if you repeat the abstention experiment for ENSO, but set the uncorrupted fraction to 50% or so, do you get a U shape in the error for the abstention network?
It's not a U shape. So we played around. So here I have it be about 30% for the uncorrupted fraction. But if you change that uncorrupted fraction, what it changes though is that it does the best compared to the baseline in that middle 50%. That's what you mean by U. It's not a U. It's because it can still start then selecting the best of the best. So which were the easiest ones to learn as you continue to have a lower coverage, but it does outperform the baseline the best at that 50% level. I
see. So more questions. So let's see. If you repeat the abstention experiment for, I think it's a follow-up. If you repeat the abstention experiment for ENSO, but set the uncorrupted fraction to 0%, does your method correctly say there are no cases to abstain?
So in this case, actually, I'll push back. This is a great question. I'll push back on the concept of, does it correctly say there are no cases to abstain? So I'm going to push back a little for two reasons. One, I've intentionally trained a relatively simple network. I didn't go into the details here, as we would in geoscience, where we don't have a ton of samples. So we don't have a lot of samples and we don't have a complex network. What this means is there are still going to be some predictions that the network finds easier than others, because this particular nonlinear function that created our synthetic data set has certain samples that are easier to predict than others. So in that sense, the network still will identify the particular samples that it knows it will get right versus those that say it waffles around 0. So in that sense, no, it doesn't say I'm never going to abstain. It will start to select the ones that are easiest to predict, which is why I think it's useful to be able to set the abstention fraction yourself as a user if you prefer.
Actually, this is great. So there's another question, Libby. in regions of absentia in the predictions, what opportunities exist for developing new mechanistic models?
Right. Okay. So what we've done, or what we've been doing in my group is linking back to something Vipin mentioned in his opening remarks, was about explainable AI. So that is, once you have a network that has said, this 20% of your samples was way easier to predict. Sorry, this is in regions of abstentia. Okay. Well, I'm going to finish what I'm saying and then I'll move back. So in regions where it was easy to predict, you can actually use explainable AI potentially to go back and try to understand what about the input made this an easier problem, or what about the output made this an easier problem. And in doing so, we are actually using this to identify physical mechanisms in the climate system that maybe we didn't appreciate led to predictable behavior. In this case, this is asking in regions of when it abstains. So one can do the same approach and ask, using explainable AI, why did the network think that this would be a hard problem to predict? Where is that noise coming from? I will say a downside, however, is it's putting all of the hard or abstained samples into one bucket, if you will. And so there could be multiple reasons for why the network is abstaining on a different set of samples. And so pulling those out to try and say, develop new mechanistic models could be tricky, because there could be 5 different necessary models hidden within there. So I don't have a great answer for that, other than I think this is what our job as scientists is to take what, say a method like this machine learning approach and now do science with it.
Great. I actually have a question, Libby, which is probably a bit more general in scope. So there are these deep generative models that people have been playing with for the past 6-7 years. They have been very active. They do pretty amazing things in terms of generating samples which look realistic, but they are very bad at getting the uncertainty right. I mean, there are papers starting to come out. So do you think this approach may help improve the deep generative models, including VAEs, normalizing flows, GANs? There's a whole bunch of different approaches in there that they can learn from in order to calibrate the uncertainties better? This is a more general question, but
sure.
It seems quite exciting.
So you know more about that world than I do. I will say, even the baseline approach of just having, of taking a regression problem from being sort of deterministic into being probabilistic alone would likely get those a certain distance. While I think the Kennedy abstention networks, we have some nice examples showing that it just outperforms the baseline. I want to stress, I think the baseline is pretty good compared to what we were in my community were doing before. So I'm not sure, if the community that's doing these generative, modeling are already considering sort of that more baseline approach, then maybe this will give it a little bit of a leg forward, but I don't know how big of a jump it will actually be if they're already incorporating, some of this simpler stuff. I think, to me, where this really shines is it looks at the data set the way someone like me as a domain scientist looks at the data, which is really saying, I don't expect us to ever make a perfect prediction. Why am I training my machine learning method to make a perfect prediction every time? And I think that's maybe where the biggest benefit is of this, is changing that mindset a little bit. I think might take us somewhere.
Yeah, great.
Thanks.
I have more questions for you, Libby, but I want to quickly make an announcement that we have a slight change in schedule. So our next speaker will be Jordan Reed. So we are moving him up. There was a scheduling conflict. So we will, after we are done with the Q&A, we will have Jordan start. So just so the attendees know that there's a slight change in the schedule. I'll actually go back to the questions. Libby, there are actually more questions coming your way. So what are some of the applications of the CAN? Has it been applied to other phenomena other than ENSO?
Great. So this is work. I mean, this work is still in review. We finished it about 3 months ago. So the short answer is no. The longer answer is I have multiple members of my group starting to apply this to different predictability problems in earth science or in climate science. For example, sub-seasonal prediction. So how do we use the information in the tropics, for example, to predict weather over the United States in the coming weeks? We're using it to look at decadal predictability. How can we use information from the ocean to understand how, say, precipitation patterns might change in the coming years? But again, those are forecasting type applications. I really think this can be used even beyond phenomena, just any data set that has noise and a signal buried somewhere within it. This might be useful. But there, I don't have anything published because we're only just started this in the last 2 months.
All right, great. I want to do a time check. There are more questions, Libby, for you, but I think we'll move on to the next speaker. So Ime, do you want to introduce Jordan?
Thank you.
Sure.
Thank you so much, Libby.
Thank you. So as you know, we had a slight change of schedule, and so Jordan Reed was so nice to say he could move up. So Jordan Reed from the United States Geological Survey will be talking to us about perspectives from the US Geological Survey about advancing water prediction with knowledge-guided machine learning partnerships. Jordan, take it away.
Oh, great. Thank you, Amy. Apologize if you're tuning in for Elizabeth Barnes or Professor Barnes' talk. I really look forward to what she presents, and she just gave an excellent talk, and we're switching time slots here, so I'm presenting a bit earlier, but hope you were able to tune in to the talk right before this, as Libby once again gave an excellent talk. So I'm here to talk today about advancing water prediction within the US Geological Survey, specifically through a number of different partnerships and collaborations. And I'm giving this talk from the perspective of the USGS Water Mission Area. I run a data science branch and oversee a collection of teams, many of which who are working very directly in this field of advancing knowledge guide machine learning. So one thing that might get you a bit hungry, maybe a bit too hungry before we step into the afternoon break, is this slide. So I apologize for that in advance. It's already making me think beyond my breakfast into what I might have for an afternoon snack. But this image really connects to the core message that I'd like to share today. So if you look to the right side of this slide, tomato soup is creamy and tangy, and grilled cheese on the left is rich and salty, but alone, the two of these are underwhelming. Together, however, they're a complementary team that offers a really rich flavor profile, which didn't exist when the two of them were on their own. Tomato soup and grilled cheese go hand in hand, and we know that they work best together. But some pairings, like the relationship between a federal science agency and academic partners, might not be that obvious. So as walking you through this presentation today, I'm going to try to make those connections clear. So how can collaboration totally shift the possible outcomes of a situation? And how does tomato soup and grilled cheese relate to water science and machine learning? There are a few ways that I'm going to address this question today, and we'll return to the grilled cheese metaphor at the end of the slide. So let's talk first about collaboration and how it relates to our topic of machine learning, more than grilled cheese does. We can take two things that as alone they are useful, but in isolation they may fall short of what our ultimate objectives are, specifically applying something to complicated science questions. So in past work, we've been able to harness the power of collaboration on numerous levels, and that collaboration shows up in various places, and we'll be talking about a few of them today. So this is an image of the Delaware River Basin. This is the northeast of the United States. You may recognize a few of the neighboring states within the basin. But in order to make effective and informed decisions with natural resources, such as those within the Delaware River Basin, we need awareness of possible future events. and the understanding of what likely happened in the past, such as the outcomes of prioritizing water for drinking and the impacts that might have on aquatic habitat, such as the habitat for these cold water trout that are pictured below. But our current modeling methods often fall short of providing adequate information to address the problem. So we use a combined method to more accurately answer pressing questions like, do we release water or not from these reservoirs? So New York City reservoirs provide drinking water for approximately 15 million people, but these are limited resources, and they also are used to maintain downstream habitat in the Delaware River Basin that supports a world-renowned fishery. In these reservoirs, there's a finite amount of cold water that can be released, but the downstream water temperatures must stay below a certain threshold to protect threatened and endangered species, including the cold water trout featured on that prior slide. So this collaboration, both a collaboration in modeling and across institutions, has an objective to forecast future downstream water temperatures with consideration to these water releases, thus enabling us to more accurately and precisely understand the implications of whether or not to release water. But hang on, what's our modeling method and who are we? So knowledge-based modeling, often referred to as process-based or physics-based model, defines equations that capture our understanding of how the world works. And we use these equations to make predictions. Machine learning, on the other hand, discovers its own equations based on data. In isolation, these methods can be extremely powerful, but are unable to meet our current prediction needs. So enter knowledge-guided machine learning. To improve water predictions, we've embarked on a collaboration between the best of both modeling approaches, resulting in this knowledge-guided machine learning. But who are we in these collaborations? I represent, or I'm speaking on behalf of one of the science agencies here, the Us Geological Survey. USGS collects massive amounts of water monitoring data and provides reliable science to the nation, but alone we lack disciplinary coverage, for example, computer scientists and many other technologists. We also have limited capacity for embarking on high-risk exploration, and by extension, we really have a lower capability for rapid innovation. So collaborations with our academic partners are key to disruptive advances in water prediction. The US Geological Survey is the primary monitoring and science agency for the nation's interior. That means our scope includes all of the environments of the United States, even nearshore coastal ecosystems, all the way to volcanoes. And a wide breadth of science is covered by 4 topical mission areas: ecosystems, energy and minerals, natural hazards, water resources, and a single crosscut mission area called Core Science System, which is designed to integrate across these other topical areas and provide scientific support and infrastructure such as high performance computing. But today we're talking about water prediction. So let's focus on how these early efforts to quantify water in the Western US and an evolving set of water priorities have resulted in a huge resource of Earth observations and science outcomes that are primed for collaborative engagement. So this water resources mission area is focused on monitoring and understanding all aspects of water availability and water quality, including different needs and uses of water for ecosystems and industry. The most visible part of the USGS water effort is the National Stream Gauging Network, which has been collecting continuous river flow measurements since 1889. And yet you heard me right, 1889, so well over 100 years. Through that time, over 50,000 gauging stations have come and gone, and over 8,000 remain that are used for all kinds of different research, and also used by the National Weather Service to forecast floods. Because of this real strength in the data program, there's been a historical partitioning with all kinds of different elements of USGS, going all the way from funding to different staff roles and specialization, including the strategy for how these different activities have been carried out. So if you can imagine the science of how we make measurements of the natural environment and specifically in water has evolved. There is lots of innovation to be had with designing sensors and also how we store and deliver data. These differences appear in numerous scales. So USGS has a number of different regional offices, typically at the scale of about a state or a couple states. And this difference in data, or this specific role in data, also extends all the way up to our headquarters program, of which I'm a part of, which covers the nation and its water priorities. We have two different distinct funding sources at the USGS. One that's primarily aligned with data, and the second that's primarily aligned with advancing studies. So just as USGS Water has developed strength in making and delivering observations of the water system, we've also been able to accumulate a great amount of knowledge, which we refer to as the studies program, which is really how the water system works. A lot of that is translated into numerical models, such as ModFlow, which is shown here in the left-hand side. And this division between studies and data extends all the way from, like I said before, the funding of how these two different bodies of work are funded, and also how they're designed to move forward. We have programs for water prediction, drought, and 5 others that are aligned with this studies source of funding. And then 7 more programs aligned with data, including one that's called the Next Generation Water Observing System, which we call NGWAS for short. This set of different programs is funded by the approximately $250 million congressional appropriations that go to the water mission area from Congress. So the prior slide focused on this partitioning between data and studies. Some USGS specialists focus on designing model equations as part of that studies body of work. So we, with this accumulation of all of this data from the USGS, naturally looked towards new advances in machine learning that could help us discover from data. USGS does not have traditional expertise in the most advanced forms of data-driven modeling. But of course, we're seeing all that is going on in leveraging these massive amounts of new data streams, and how data-driven models began to quite easily beat the accuracy of our designed model equations in terms of accuracy. This New Yorker example from an article showed that a deep learning model was able to be trained on the corpus of writing from the New Yorker and able to emulate the writing style of that magazine. So of course, if you're thinking about modeling the water system and you see a model that can approximate a particular writing style of a magazine, by extension, you imagine that a similar modeling approach might be able to, for example, provide a more accurate estimate of the timing of snowmelt than our current modeling equations that are designed. So that, of course, led us into these strong collaborations that I mentioned earlier. We knew that there was a great deal of promise in leveraging advances in deep learning, but at the time, of course, lacked the expertise to embark on those. So combining our efforts, our understanding of these knowledge-based or designed models with the vast data resources of the USGS, we connected with our academic partners. And of course, instead of looking at modeling as a trade-off between design and discovery, looked at it as a collaboration between design and discovery. So instead of or, it becomes and. Our early work looked to draw contrast between these different models. So a model that is designed based on an understanding of the way a lake or reservoir behaves. So it's conservation of energy. So the incoming and outgoing energy fluxes as a lake interacts with the environment are captured in equations. And that model can be driven with inputs of weather. One advantage of this type of model is that when there are no data or very little data, it can still provide usable predictions. But of course, as we add more and more data, this model isn't as available or isn't as able to leverage additional information to improve the accuracy of its prediction. And then of course, the contrast is a purely data-driven model, or in this case, a neural net is able to beat a designed model or a process-based model when given enough data. But of course, if we remove more and more data from this model, which is typically a data-hungry model, it will fall apart and definitely not be able to perform at all when we confront it with no data that would be available for training. So of course, the collaboration between design and discovery becomes knowledge-guided machine learning, which is able to take advantage of the best of both worlds. So models that are both designed and are allowed to discover and modify responses to the inputs. So coming back to this modeling objective, and this is one of many different modeling questions that may come up, but of course is the feature use case of this talk, whether or not we want to release water in this Delaware River Basin from reservoirs. And this specifically is a decision for reservoir operators. The fruits of this collaboration and really the foundational building blocks to make this question something that can be answered have come in the form of a number of different modeling architectures and advances as captured in these papers throughout the last 4 years. So these initial papers that I'm highlighting here provided new knowledge-guided machine learning methods approaches to make stream and lake water quality predictions more accurately. And these were critical advances because they were able to make predictions that were accurate enough to be usable for decision makers. And those decision makers were able to communicate their needs for accuracy of model predictions to us in the form of our forecasting problem with water releases, having a root mean squared error below a certain threshold for a decision, and also in other collaborations with fisheries researchers and managers to have accuracy root mean squared error below 1 degree C in order to make informed decisions about the future and past of a inland fishery. Next, these models were tested or modified in a way that we were able to make predictions out of bounds. And these two papers highlight two very different applications of out of bounds predictions. So the 2019 paper in Water Resources Research showed us that by exposing these knowledge-guided machine learning models to synthetic predictions from a knowledge-based model, we were able to make predictions in an extreme period that was held out from the training data. So in that case, it was withholding summer training data from the model and asking a model to predict summer water temperature conditions. And as you can imagine, those are quite different than the adjacent seasons of spring and fall, and definitely quite a bit different than wintertime temperatures. And then the paper by Jared Willard that just came out this year and also in Water Resources Research used metatransfer learning to decide which trained model could be applied to an unmonitored system to maximize the accuracy of that model on that otherwise unobserved system. So really great advances that both provide extension to where these models can be used and also provide additional confidence in their use. And also in working with decision makers that are using predictions, it's critical to have some estimate of uncertainty in those model predictions. In the past, that has been lacking from many of our use cases for modeling, including process-based or knowledge-based models, and definitely also in data-driven models. But that's a critical piece of information that is necessary for the use of these predictions. And so in ArcaDaw's 2020 paper, there was a dropout uncertainty quantification method used to estimate uncertainty in a Kgml approach. And then also in Jake Zwart's forecasting paper, uncertainty was also quantified as part of producing forecasts. And so these different pieces led us to the ability to combine knowledge-guided machine learning with data assimilation to produce near-term forecasts of stream water temperature that also includes the impact of that decision, whether or not to release that cold water that is contained within a reservoir in order to cool downstream habitats. So coming back to that original question that we have. And I also point you to Sam Oliver's presentation in the aquatic session that is coming up later this week. So in summary, these knowledge-guided machine learning partnerships between USGS and our academic partners are really creating new modeling strategies for solving real-world problems that are integrating their way into USGS scientific strategies. So for example, knowledge-guided machine learning, or as it's referred to in a lot of these strategic plans, process-guided deep learning, is already a priority in several of these new USGS water programs. It's part of current projects and part of the plans of future projects, which will tap into this new modeling approach. Also, in these communities of practice, we're exchanging data, code. We're working together to make these models more reproducible, more transparent, and understandable as we collaborate openly with publications and also with data releases and code releases that accompany those papers. And lastly, as a major boost for the US Geological Survey, the outcome of having Kgml science be a big part of training the next generation of water leaders. So some examples of that, Allison Appling, who is a co-lead of the aquatic session later this week, is now running the strategy for the application of machine learning in the USGS water mission area, and is overseeing the launch of 5 new projects next year that will use knowledge-guided machine learning as part of their modeling architectures. Also, Sam Oliver and Jake Zwart were able to jump on this opportunity to make forecasts for water temperatures in the Delaware River Basin and create successful models and data releases for that. And lastly, we've been working with a graduate student, actually with several different graduate students, but one I'd highlight is Jared Willard out of the Kumar Lab, who's doing a USGS internship on Kgml work and will be soon in the fall moving to work with DOE as part of a fellowship. So Department of Energy is another federal science agency, which is also continues to be very interested in leveraging knowledge-guided machine learning for their purposes for advancing their models. So returning back to our grilled cheese and tomato soup, as we're now getting ever closer to the lunch break, I wanted to remind you of this collaborative thread that's been woven throughout this talk, which is these two things, which are pretty great, but combining them thoughtfully through collaboration can make them even better. And just a few things that we touched on. So the posture of a federal science agency being a natural complement to the academic opportunities for rapid innovation and high-risk testing. Also, the pairing between a long-running data program, such as what the USGS has, and also being able to use that to train and build models. And lastly, of course, is the basis for this workshop. So knowledge-guided machine learning. So the idea that we take knowledge-based models and can combine them with machine learning approaches to create a new approach that is even better with this collaboration in mind. So thank you.
Thank you so much, John. So here's a question for you, Insider. John, if someone at a university is interested in working with USGS or other federal agencies, how do you suggest getting that collaboration started?
Yeah, that's a great question. So USGS has a couple of different funding vehicles that make that collaboration with funding possible. We have a competitive set of grants that come out of the Water Resources Research Act, which is one of the congressional appropriations that I didn't refer to, but those competitive grants come out once a year, and the present pot for funding is at $11 million. And each one of those grants needs to have at least one USGS partner as part of the proposal. So that's one way. A second way is to engage directly in collaborations by reaching out to connect with anyone you might know from USGS, and that could be emailing me, it could be emailing Allison or Sam or Janet Barclay, who's also presenting later in the week, or anybody that might overlap with your particular area of interest, and talking to them about collaboration, depending on whether or not that collaboration would require funding on your part or not. Kind of sets it up for a different level of engagement. We have the ability to fund graduate students and also academic PIs through other agreements with universities, and that's actually quite a bit streamlined for land grant universities as well, but not restricted to land grants. So I would say definitely reach out to us.
Great. The next question that came in, are Kgml approaches suitable for multi-objective water resources problems?
Sorry, could you repeat that one?
Sure. Are Kgml approaches suitable for multi-objective water resources problems?
Oh, great question. Apologies, coughing a little bit. So one of the papers that I glossed over when going through the bullet points was led by Jeff Sadler, which is a multitask modeling approach. So the idea that there'd be two target variables. So in the case of Jeff's work, it was stream discharge or river flow, but also stream water temperature at the same time, and kind of the competition between those variables, and also the information sharing that can be possible when predicting variables that have some physical relationship to one another. I would say that story, the results of that work in that paper, and it's available via archive if you want to take a look at it right now. That story is complicated, as many modeling stories are, in that multitask or multi-target approach is advantageous in some ways, but can be overly complicated in other ways. And instead of getting into the details of what those may be, I would suggest you check out that paper. But the bottom line there is, when there's lots of stream temperature data and lots of discharge data, that those two variables can be complementary to one another for predictions. But there's also additional architectures that can leverage that information as well.
All right, we have 1 more minute before the break, and we have 2 more questions. So I will take the most popular question, and hopefully, Jordan, maybe you can answer the other one in Slido later on. So the most popular question is, what is the difference between working in federal agencies such as USGS or in university as new graduated young scientist?
Great. There are real differences between working for a federal science agency and working in academia. I would say the cliche difference is intellectual freedom. So in a federal science agency, we are bound by the priorities that are funded. We have a set of programmatic priorities that we need to stay aligned with, and those constrain us a bit more than academic PIs. That's just the nature of the differences between those two. But I would argue that we do still retain a lot of freedom to explore approaches and different science objectives within those priorities. Not as much as academics, but still a good bit of opportunity to explore. There's also another key difference, I would say, that's related to stability or longevity. Our workforce model is built on a much longer rate of retention on average than the academic model, because we don't have students coming in and leaving after, say, 2 to 3 to 5 years. Our employees stay for longer. That has positive impacts and negative impacts. Positive impacts is we're able to build and invest in employees through time. The negative impact is we have a slower rate of refresh and kind of new ideas and new people coming in, because those new employees start at a lower rate than academic graduate students. And by that I mean we're only able to hire so many individuals per year because we have a longer retention and only so many slots open.
Great, thank you so much, Jordan. And thank you again, Libby and Jordan, for being flexible and moving up in time slots. Just an announcement, we will take a break for 15 minutes in a second. And as you noticed, our schedule changed a little bit. So what will happen after the break is that the first speaker after the break will be Xiaowei Zhao. And then the next speaker will be Zainong Jin. So they're both moving up one slot. And then at the very end, we will have Animar Anand Kumar, who is our keynote speaker. That will be the last speaker today. So just everybody keeps on moving up, and Animar is at the very end. So with that, we will take a 15-minute break, and we will see you exactly 10 minutes after the hour again. Thank you again for being flexible. Thanks. Bye. All right, welcome back from the break. Could we just get that slide back that we just had a moment ago, please? Thank you. So as you can all see, we now updated our schedule here, and thank you everybody for being flexible. As you see, we now have Kgml and Zhenong Jin after the break, followed by Anand Kumar. So we will right away proceed with the first talk. It's my pleasure to introduce Kgml, who is an assistant professor in the Department of Computer Science at the University of Pittsburgh. But he's been with this project for a long time, because before that he was actually at the University of Minnesota and was one of the starting members of this. So with that, Kgml, please take it away.
Yeah, it said I cannot start screen sharing. Okay, yeah, now I should be able to. Can you see my screen? All right. So, hello everyone. This is Kgml from the University of Pittsburgh, and my talk today is going to be on this physics-guided machine learning for model initialization using physical simulations. So first, I want to give some context about these two types of models that have been very widely used in many scientific problems. The first one is called physics-based models, or sometimes they are called like mechanics models or process-based models. And these types of models have been built mostly based on our current understanding of many scientific theories. And at the same time, actually, they also use a lot of like simplified representation, like approximations for some parameterization processes, either because some processes are just not fully understood by people, or they're just too complex to be directly modeled. So that's why these physics-based models, their predictions are not always accurate. And also another limitation of this model is that they always make some simplified assumptions. For example, many models assume some physical parameters are static over either space or time. And on the other hand, machine learning models these years have found a lot of success, especially people have found that these machine learning models usually can outperform existing physics-based models if we are provided with sufficient training data. But in practice, in many scientific problems, it's going to be very costly, very expensive to collect a large amount of training samples. And also many physical processes, they are very complex. So they involve a large number of physical variables. And this relationship between these variables can change over space and over time. So it's very hard for machine learning models to automatically extract this complex relationship from data if we are only provided with limited training samples. And another issue about machine learning model is that they're mostly focused on mining the statistical relationship from data, but these learned patterns from this available training set may not be able to generalize to scenarios that look very different from our training samples. So given this, the power and the limitations of these two types of models, so in recent years, there's a growing interest of building such a physics-guided or such a hybrid physics and machine learning models. So in our recent survey paper, we have summarized several different approaches for integrating physics into machine learning. And here we list a few of these very popular methods. So first, one can build a new loss functions to penalize those predictions for some intermediate variables in machine learning model that significantly violate these established physical laws. And the second approach is that we can build new model architecture or some neural network architecture to embed these known physical relationships amongst different physical variables. And the third approach, which is the focus of our talk today, is to transfer some physics to inform the initialization of these machine learning models. So for example, in previous studies, people have used this simulation data produced by some physical models to pre-train the machine learning model. So the idea is that if we can pre-train the machine learning model using a large amount of simulation data, then it's very likely that this machine learning model can get much closer to its target solution. Then it only requires very fewer amount of training samples to fine-tune itself to the target solution. But there are still several limitations of these pre-training or this initialization method. So first limitation is that most of these methods, they require some high-quality simulations. So, but this is often not available in many scientific problems because of this uncertainty in selecting these model parameters. So here we give an example for lake temperature modeling. So in this example, if we select a darker clarity value for these lake systems, then we find these simulations produced by this physical model. Actually, here we use the general lake model, which is considered to be a state of the art for lake temperature modeling. And these simulations produced by this model, we can find it's much lower than the true observed water temperature and in the middle layer of Lake Mendota. So this is because this clarity parameter actually controls how much solar radiation can penetrate downward the lake surface. And another limitation is that most of these existing approaches, they actually use physical simulations always in a separate training stage. They either use it to simply pre-train the machine learning model, or they can use it to augment the input drivers, but they never fully explore the relationships between these simulations and true observations. So in our proposed method, so we have two general objectives, and also this proposed method has such a two-stage training process. So in the first stage, we want to pre-train this machine learning model using multiple runs of simulation data that are produced under different physical parameters. And our objective here is to extract some general physical relationships that are encoded in these physical models. And the second stage is we're trying to fine-tune this pre-trained model using the true observations. But at the same time, we also want to explore the similarity between these observations and simulations of different parameter settings. And also we want to identify the variations of these physical parameters over space and over time. So this figure at the bottom summarizes the entire flow of this proposed method. So at the beginning, we are provided with the structure of these dynamical systems, or this spatial dependencies across different locations in the systems. And for each location, we are also provided with a time series of these input drivers over time. And then we have access to a physical model. And using this physical model, we can produce multiple runs of simulations using different physical parameters. And then by jointly learning from multiple runs of simulations, we can pre-train a customized machine learning model. And after we get a pre-trained model, we can further fine-tune it using observations through a contrastive learning process. So first, let's look at the pre-training phase. So the pre-training aims to extract some general physical knowledge from multiple runs of simulations. But before that, we want to first construct such a customized model architecture so that we can reflect how these physical parameters affect the model predictions. So ideally, we find most of these physical parameters, they actually determine how the system states react to some external input. So this means, like, if we consider there's a sequence of these evolving system states over time, so these physical parameters actually, they can be used to filter the information from these different external inputs, and then this filtered information can be used to update the system states. So based on this consideration, we built such a customized model architecture. So we call this as spatial temporal network, or STN. So in this model, we have two sets of model parameters. The first set of model parameters is called simulation specific parameters, theta. So this theta is different for different run of simulations. And this data is mostly used to create a set of gating variables in this architecture. So these gating variables are used to filter the information, for example, from the current climate drivers, or from the spatial neighborhood, and also from the past history. So they are mostly used as some filtering variables in this architecture. And the second set of variables is called simulation invariant model parameters, phi. And these model parameters are shared across different runs of simulations. And based on this architecture, our pre-training, the goal of pre-training is to estimate the initial values of these two sets of parameters. So this method is actually inspired by this ML, or this meta-learning algorithm in machine learning. So so the idea is that if we are given multiple runs of simulation data, and if we consider these multiple runs of simulation data are distributed in the space, and then our goal is actually to find a model in the middle of these multiple sets of simulations, so that this model can be quickly adjusted or adapted to each run of simulations. And to do this, we will first divide each set of simulation into two separate training and validation sets. And then we will first use the training set to update the model parameters. And then we use the updated parameter theta to calculate the loss on the validation set. So the final pre-training loss will be defined as a sum over all these different validation loss on all of these different set of simulations. And after we get the pre-trained model, we will further fine-tune this model using observations. So I'll skip some details here, but the basic intuition is that if we consider some simulations are produced using more accurate parameters, using more accurate physical parameters, then there's a higher chance that these simulations are is going to be more similar to true observations. And on the so in contrast, if some simulations are produced using less accurate parameters, then there's a higher chance that these simulations will be farther away from true observations. So there's such a contrast of similarity between observations and simulations. And that's why we build such a similarity mapping between true observations and each set of simulation one. And also we will use a contrastive loss for the fine-tuning phase. So this fine-tuning process can give us not only a final fine-tuned predictive model, but also as a byproduct, it is able to provide such a similarity mapping between observations and different sets of simulations. So we evaluate our proposed method in two different applications. The first one is to predict the water temperature in Lake Mendota. So Lake Mendota has a depth of 25 meters. So we try to, we will predict the water temperature in each depth layer of these lake systems. So we will train the model using data or using observations from this period, which has in total about 8,000 observations. So the observations here can be really sparse. That means these observations may be available only on certain depths layers or on certain dates. And then we will test the model in another period. And to generate simulations, we will use simulations generated under different geometry structure of these lake systems. So for example, we have tried using cone and barrel martini, these different shapes. And these three shapes actually have been very widely used in lake modeling community. And also we have tried generating the simulations using different values for clarity, water clarity in the lake systems. And the second application is to predict the water temperature in river network, Christina River Watershed, which is a subset of Delaware River Basin. So here in this river network, actually, the rivers are considered to be well mixed because they are shallower, but we need to make predictions simultaneously on all the river segments. So we will train the model using data from this period, which has in total about 34K observations, and then test in another period. And then we generate simulation data using different parameters, using the parameter of these, by varying this parameter values for this average groundwater residence time. So this parameter, this residence time actually determines how quickly this groundwater moves through the aquifer and enters the stream. So if we have a lower value for this residence time, then there's a higher chance that this groundwater temperature is going to be more similar to the recent air temperature. And we will look at the performance on several different aspects. The first one is we will check the performance of pre-training and fine-tuning, especially if we only provided the sparse data. And the second one is we want to see if we can get any interpretation of the learned similarity relationship between observations to different simulations. And the third one is we want to check whether these models can indeed generalizable to different scenarios. So first, let's look at the pre-training performance. So here we show the performance in predicting lake water temperature, and we show the simulations and predictions made for each different layers of this lake system, Lake Mendota. And the first column shows the learning performance using simulations generated with different geometric structures, cone, martini, and barrel. And the second column shows this, the learning using simulations produced using different clarity values, normal, darker, or clear. So we can see that on the lake, at the lake surface, most of these simulations or predictions, they can do a pretty good job in matching those true observations of water temperature. But in the middle layer and the bottom layer, we find the selection of these model parameters becomes much more important. because if we didn't carefully select this, like the geometric structure, we can see the simulations can either over-predict or under-predict the water temperature. And something we find is that the predictions made by our pre-trained model, this red curve, is always in the middle of these three sets of simulations. And remember that in our pre-training phase, we have no access to true observations. So that means the model has no idea of which of these three sets of simulations that they are more accurate to this lake system. But this pre-training is simply trying to generate or trying to extract some more general relationships or some patterns that are shared across these three sets of simulation data. And here we show the performance of fine-tuning. So after we fine-tune this, after we get the pre-trained model, we fine-tune it using 2% of observations. So remember, we have about like 8,000 observations in the training time. So we use 2% of data, that is about like 160 observations from the training period. And even just using this small number of observations, we can get much better performance in matching true observations. So we show this fine-tuned model using the green curve. And now we can see this green curve can match these observations much better. And even if we know that pre-trained model is not always perfect, but it is still able to extract some general physical relationship from these simulation data. And that's why we only need very few amount of training samples to close the gap between the red curve and the green curve. And this table simply shows that we also use a lot of different sparsity levels from 0 to 2% to 100% for this test. And in most cases, we find our proposed method give us better performance. And now we want to check what's the learned similarity from this contrastive fine-tuning process. So this figure shows the similarity between observations and different clarity values over different depths. And also this one shows the similarity between observations to different geometric structures over different months. So actually from here, actually these results give us some very useful information because we know that most existing lake temperature models, actually they assume a single or static clarity value across all the depth layers. But from these results, it actually suggests that we may be able to select different clarity parameters for different depth layers. And this is actually consistent to our understanding of this natural environment. And this figure actually shows that these observations are more similar to the cone shape in the summer period, but it's closer to the barrel shape in the fall and winter time. And one hypothesis here is that this fall cooling period and this under ice temperature may be better simulated using the barrel shape because the barrel shape has a slower cooling process, which may be more appropriate for this lake system. And for lake temperature modeling, for river temperature modeling example, so we find most rivers in Christina River watershed are more similar to the simulations produced by this lower value of the residence groundwater residence time, and also they are more similar to this lower value in the spring period. So actually, this is consistent to our or some other previous study which have shown that in this area, many of these shallower groundwater, so shallower groundwater usually have a lower value of groundwater residence time. So this shallower water usually contribute more in the springtime compared to other time periods. So finally, we also verify the generalizability of the model. So we train the model using data from, so this is for the lake temperature modeling. We train the model using data from colder seasons, spring, fall, and winter, and then we test the model in the summer period of the test period. So the second column here is more like a baseline where we still train the model using all the data from the training period. But the first column shows the performance of these generalization tests. So we expect an increase of prediction error from the second column to the first column. But we can see that our proposed method actually gives us a much smaller increase of prediction error in this case. So some of our future directions, so we will explore learning from a larger range of parameter values, and also we will try to learn from simultaneous variations of multiple parameters. For example, what if we vary the value of this geometric structure and also this clarity value at the same time? And also we have several ongoing projects which involve some similar methods. For example, we can not only identify the most suitable physical parameters, but also we can see if we can use similar approach to identify the physical models or some physical formulas that are more appropriate to use under different scenarios. So that's all about this talk today, and thanks for listening. Any questions?
Thank you so much, Kgml. So the first question in Slido is, are observations also being used to bias correct the pre-training simulations so that they are closer to the truth to begin with?
Yeah, actually, I think that's actually a very good point. So let me just go back to here. Yeah. So I think there are several approaches for using this or combining the simulations and true observations. So I think here we consider doing this in this two-stage process, pre-training and fine-tuning. But in some other domains like climate science, I've also seen people have used the observations to first do a bias correction of these simulations, and actually that's helpful in multiple purposes, especially for reanalysis. So that would give us some good historical data. So I think that's a different view, but it's definitely relevant, and it's also a different example for how to find the relationship between observations and these simulations. Yeah, I think we will keep it. I think we consider comparing some of the baselines. For example, if we first do a bias correction of these simulations using observations and then do a pre-training or use it to guide the learning, that may give us better performance.
Okay. Next question is, what is the difference between the proposed network and graph neural networks?
Yeah, it's actually relevant. So this proposed method, it actually has this recurrent component and also a graph convolutional component. The graph convolutional component mostly used for capturing this spatial dependencies across different locations. So the major difference is that we consider, so there are lots of parameters in this architecture, and we divide these parameters into two different sets, theta and phi. So these data values, they're specific to each set of simulations. So that means the parameters used to calculate these scaling variables, they're different for different simulations. But some other parameters, like these parameters used for output gating variables or some other fully connected layers, those parameters are shared across different simulations. So mostly, I would say this architecture itself it has its own graph component, which is exactly the same with existing graph models. But we're trying to use these two different sets of parameters to reflect how these physical parameters play a role in this prediction process.
All right, there are two more questions, but we only have 1 minute left. So if I could get a quick answer on this question.
Sure.
There are many ways to fine tune. Is there a particular reason you favor your particular approach?
Yeah, that's a good question. I think the major, I think that depends on the different applications, but I think here our major concern is some simulations are more accurate in this system, and some simulations are not very accurate. So that's why in our fine-tuning phase, we want to produce this byproduct of the similarity mapping, and that's why we use this contrastive learning process. But definitely, we in our experiment, we have compared to several different other fine-tuning process. And we have shown this method gives us better performance, at least in our applications.
Thank you so much. And Kgml, feel free to go into Slido and answer the one question that's still left. And with that, thank you so much. And I will introduce the next speaker. So our next speaker, I'm pleased to announce, is Zhenong Jin, who is a professor at the University of Minnesota. He was actually trained as an agroecologist, and his research integrates process-based models, remote sensing, and machine learning approaches. And I also will mention that he was a lead crop scientist at Atlas AI, so he also has industrial experience. With that, I will turn it over to Zhenong Jin. Thank you.
Okay, thank you. Really glad to present here to share our experience when investigating the Kgml approach for agriculture. And today I will give 2 examples for modeling N2O emission. Is a nitrous oxide, a kind of greenhouse gas, and eco-hydrology. And I would particularly thank our contributing author, without whom this talk is not likely to happen. So why agriculture? Because agriculture is at the hotspot for fighting climate change. So agriculture contributes to about 1/4 of the global greenhouse gas emission, and with 15% comes directly from agriculture production, and about 10% through the land use change, mainly happening in the tropical region where people converted tropical forests into the cropland. And in the US, okay, so agriculture contributes to about 10% of total emission. And if we further break it down, the 10%, we see nearly half of them come from the soil fertilization, maybe when we apply nitrogen NPK fertilizer. Okay, and the majority of the emission is in form of N2O, nitrous oxide gas. And N2O is about 265 times more powerful than carbon dioxide as a greenhouse gas. Now, the problem with N2O emission, the farmers usually over-apply fertilizer, because with the changing weather condition and the interaction with soil, it's just so hard to predict what's the optimal nitrogen they should apply every year, every season. So as a way to do the insurance, they usually apply more fertilizer than necessary, because fertilizer is cheap, but yield losses caused by under-fertilization is a problem. And this usually leads to over application of the nitrogen fertilizer. And then this is a serious problem to the air pollution, to water pollution, and also land degradation. And recently we saw a surge of interest in sustainability, and many of the larger corporations, they have committed to achieve net zero emission by 2030. For example, here, Cargill, all the food industry company, have agenda to cut their greenhouse gas emission, and Microsoft, Amazon, they want to reach net carbon neutral operation by mid of the century. Now, carbon offset from agriculture is one of the popular solutions to mitigate the carbon emission. And according to the report by Soil Health Institute, if farmers can change their current practice, there's a huge potential to cut the greenhouse gas emission. For example, if they optimize the grazing management, they optimize the nitrogen management, if they adopt a cover crop to sequestrate this carbon dioxide from the atmosphere, or if they adopt a no-till change from the conventional tillage practice as a way to present the soil carbon to break it down and then gradually release back into the atmosphere. So here's both a surging demand for carbon offsets, and agriculture can provide a potential supply. But there's also a question or concerns by a different group of scientists who suggest to say, okay, even if you do this kind of practice, because there are not, many of them are not permanent and vulnerable to goes back into the atmosphere. So the actual carbon sequestration potential by agriculture may be small, or much smaller than what the advocator are suggesting. But for sure, all those practices, they belong to the conservation practices or regenerative practices, which benefit to soil health and more broadly to our environments. But regardless of the debates, the agricultural carbon market is already around the corner. It's happening in Europe, it's happening in China, it's happening in the US. So here is a brief illustration of how agricultural carbon market works. It starts with data collection through soil sampling. We set up a benchmark, like how much the greenhouse gas emission is for a particular field. And then the farmer will adopt the changes. And currently the suggested practice is adopt cover cropping, change from tillage to no-till, reduce nitrogen fertilizer, and diversify the crop rotation. And next, a third-party verifier will come in to verify the carbon removal, but it is a challenge task, which we will discuss in more details later. And then the carbon trading company comes in to buy the carbon credit from farmers and then sold them to the buyers, mostly corporations who want to mitigate or cut their greenhouse gas emission. And once the carbon credit was sold, the money goes back to the farmer for to reward their practice change. Now, a concern here is action does not equal to outcome. And what that means is, for example, two farmers in the southern US versus a farmer in Minnesota, if they all add cover crop, the farmer in southern US would expect to increase or sequester 1 ton carbon dioxide per hectare per year, but in Minnesota, it's likely to be only 0.2. So the same action will lead to very different outcome. And even within the Minnesota, the two nearby fields would have a very different outcome. This makes the verified carbon credit a particularly important a step to make the market transparent and rigorous. So here comes the Congress. They have just passed the bipartisan bill called Growing Climate Actions, Growing Climate Solution Act, which asks the USDA to create a certification program and help the landowner, farmers, ranchers, and foresters to navigate through the growing agriculture carbon trading program. And accurate and cost-effective methods for quantifying carbon credits is a fundamental to the agriculture carbon market, because we want to make sure like all the claimed carbon sequestration is real, and we pay every individual farmer fairly and accurately. So this is the quantification is critical to make sure the program does not become an unverified subsidy. And here I use Untitled as an example to illustrate what options we have currently for the greenhouse gas emission. And as you can see from the lower parts, emission factor, it's easy to use. You just multiply by a coefficient that turns the nitrogen fertilizer into Untitled emission. But the uncertainty is huge. Airborne sensing, mostly by sometimes by hyperspectral sensing, it has a huge potential, and people are excited about this. But overall, the technology is at early stage. And process-based modeling, which simulates the complex feedback between soil, water, atmosphere, crop, is a widely used tool to estimate the greenhouse gas emission. But because of the uncertainty in model inputs, model structure, and model parameter, we expect to see a large errors in any of the estimates. Okay, so what about the Kgml for modeling Untitled? And to start with, let's ask a question like why estimating Untitled is so hard. Now, Untitled, briefly, it's coming from two processes, mainly denitrification, but sometimes it could also come from a reaction called the nitrification. And Untitled emission is hard to estimate or model because it has a hot spot and hot moment pattern across the landscape. And this is because Untitled is controlled by a range of biotic and abiotic factors. At the very bottom, that's the weather management and the initial soil status. And then in between, there are many intermediate variables like soil water temperature, soil texture, and how the microbes come in to interact with all the abiotic factor, and this interaction determines the oxygen-nitrogen availability, which ultimately drives the enteral fluxes. And so because of the hotspot hot moment pattern of the enteral, we explored lots of different structures for the Kgml model. And one promising case we found is from our past work by Dr. Vipin Kumar's group that use Kgml to simulate the stream flow. It's similar to enteral because you also expect to see a hotspot hot moment pattern. So the benchmark here is a black box deep neural network model, LSTM, and the experiment here is trying to reproduce a 1,000-year simulation from a SWOT model. Okay, now the domain knowledge can provide guidance on the machine learning model through multiple aspects. The first is simultaneously simulate the interrelated variable. And the second is to distinguish a state versus flux variable. And third is to describe the dependency structure between different intermediate variable and the target variable. And finally is use a physical constraint among the different model. And as you can see from the performance, the physics and the knowledge guidance does improve model performance. So this gives us hope to develop a Kgml model for enteral emission. So experiment overview, we use the synthetic data and observation data to explore feature importance and their causal relationship as a foundation to design our Kgml model structure. Now we use synthetic data to pre-train the Kgml, mainly to initialize the initial condition and the weights. And the real observation data was used to retrain the model and refine the Kgml. And the left out observation data will be used to evaluate the Kgml. We generate our synthetic data from an advanced ecosystem, agro-ecosystem model called EcoSys. So EcoSys, like many of the crop models, explicitly simulates water, energy, carbon, and nitrogen cycle. But importantly, EcoSys is mostly built on physical and biogeochemical rules, and not so much based on empirical relationship, so that you have to tune a lot of parameters. And in that way, we believe EcoSys is the ideal model to provide the domain knowledge. And we have validated EcoSys using 7 FluxNet sites for agriculture across the US. And here's the experiment we used to generate the synthetic data. Now, the real observational data. First, I have to mention the high quality enteral measurement is very limited. And and more often they only observe enteral fluxes along with a limited biotic and abiotic variables. And here, this data set from mesocosm experiment is unique because it measures enteral, but also many intermediate variables like the carbon dioxide fluxes, soil moisture, and some soil chemical indicators, so that we can use them to diagnose our Kgml model, the intermediate stage. And so we tried a different structure, and it turns out the GRU outperformed the LSTM as a benchmark pure machine learning model. And the Kgml model is developed also based on GRU, but has more knowledge guidance. And the lower part, the GRU cells are used to represent the driving variable and also intermediate states of the system. And the upper part mimics the biogeochemistry reaction that for nitrification and denitrification. So let's take a look at the results. Okay, so Kgml model, it does outperform the pure machine learning model, the GRU. And I want you to particularly pay attention to some of the peaks, which is the key aspects we want to capture, the peak fluxes. And as you can see, the red Kgml prediction can more or less capture the real observation, but the GRU in blue doesn't do a good job in many of the cases. Now, the other interesting part is out of the growing season, the GRU model without domain knowledge guidance predict a high emission peak in the winter time. But based on our domain knowledge, we know it's not likely to happen in the controlled greenhouse. So, but in contrast, the Kgml model, it's pre-trained with the ecosystem model. So it has a domain knowledge inside, does not make a fake prediction. So this also suggests the Kgml model with the pre-training to assimilate domain knowledge does do a good job compared to pure machine learning model. Now, you may wonder, how about the original agro-ecosystem model? Here's the result. Same chamber year simulated by ecosystem. And you can compare the two, R-squared, IMSE, it's worse than the pure machine learning model and also the Kgml model. So we also compare to many other tree-based model and the simple neural network model. And Kgml model is always significantly better than other benchmarks. So our next step is to expand the Kgml model with more gold standard data coming from FluxNet. And also recently, the ARPA-E has founded a smart farm program to collect the gold standard data with hot moment and hot spots incorporated in the experiment design. So we discussed the Kgml model for a mesocosm experiment, but our ultimate goal is to monitor and model greenhouse gas emission for every field across the US. So here we introduce a framework that says agricultural outcome, crop yield, greenhouse gas emission is the interaction between crop, traits, management condition, and environmental condition. Now, oftentimes, let's use a modeling a net ecosystem exchange, the CO2 flux between land and the atmosphere as an example. So oftentimes when people do the modeling, they only have environmental information, weather, soil. As you can see, the performance is really bad. And if we can collect information on management, for example, when you plan to harvest the crop and a bunch of others, you can improve the model performance. And if you have information about crop traits like the variety, the maturity group, and their responses to different environmental stresses, we could significantly improve the accuracy of model prediction. So the key here is we need to derive the hyperlocal observation, and we need a way to scaling the field collection, no longer based on sampling, but more on low-cost sensor and hyperspectral imaging as label. And we need a high-performance computing switch from process-based model to Kgml surrogate model. And this is a system solution we're proposing, because we believe now at the current stage, none of the single methods can solve the problem. So we need a harmonized collaboration between the different methods. So here I give you an example what I meant by the scalable satellite information and similarly for IoT sensors. So here is an example, 10-meter daily ET product for the US coming from Kai-Yu Guan's lab at the UIUC. And as you can see here, the best ET performed much better compared to the state-of-the-art LXET. And the nice thing about this is for any of the field, we could have a real-time or near real-time observation as long as the satellite data become available. So here, blue line is the estimation from best ET, and black is the observation. In most cases, it tracks the real observation coming from eddy covariance tower. And this is a state-of-the-art satellite product. Now, let's zoom out to revisit the big picture. Our food system currently emits about 12 gigaton CO2 per year. And if we do nothing, it will increase to 15 gigaton by 2050, even if we can keep the yield increase. So we don't clearing too much tropical land. But actually, we need to achieve a 4 gigaton per year emission target if we want to limit our global warming under 2 Celsius degree, or even 0 gigaton for 1.5 degree. So what we can do. And according to the World Resources Institute, coordinated action is needed. And it includes like reduce food waste, change the diet, and increase the food production, which mainly would come from breeding program, and increase fishery supply and reduce emission from the production. Mostly, it's would achieved by nitrogen and manure fertilizer management, and also protect and restore natural ecosystem. So many of the solution has some connection to the talks in the subsequent, the following sessions. So yeah, really coordinated efforts needed to limit the global climate change. And with that, I would thank you for your attention. And if you're interested in machine learning model and Kgml model for agriculture, we are hiring PhD students and postdocs, and welcome to contact.
Thank you so much, Denon. There are no questions on Slido yet, but I had a question, if you don't mind. So you mentioned the Growing Climate Solutions Act, right? That was just enacted in June. I was just curious, how has that changed your work? I mean, there must have been a huge influx of interest ever since that came through, right?
Yeah, definitely. So first, we expect there's a huge resources coming in to invest in this domain. And what I and my collaborators, we really believe the science community should figure out a technical roadmap where the resources should be invested strategically, because we are talking about a big number coming from the federal government. And I think now, as an example, for AI research, there's ImageNet. But for agriculture, there's not. We are always dealing with messy, sometimes trash data. So the fundamental thing we first need to do is maybe create a ImageNet for agriculture. And those should be achieved by expanding more of the golden standard data collection.
Great. And I'm pretty sure we will hear a lot more about your research based on the demand, the big demand. And now the questions come in like crazy. So here's the first question. How can you expand the Kgml application you developed?
Sorry, could you expand the question?
It's a slightly vague question, but gives you more chance to broaden. How can you expand the Kgml application you developed?
Okay, so I guess there's a let's look at the structure. First, there's lots of things to do and upgrading the structure. And we are collaborating closely with the computer science group here. And the other promising stuff, I think, is being able to assimilate real-time observational data. And there's about more than 2,000 or close to 3,000 satellites going around the Earth. So it provides a huge number of data to provide the constraint to the Kgml model. And so developing a flexible structure that is able to assimilate the satellite IoT sensor data to make real-time prediction. I think it would be very promising direction down the road.
All right, next popular question. could you use a combination of model output and observations to guide deployment of observation platforms, i.e. what quantities would be most useful to observe?
Yes, that's a very good question, and that's actually what we want to do. So partly, like earlier in this slides, we use the causal relationship analysis to identify, okay, here's a few key variables to measure, and with some initial measurements, we could have a sense of where is the hotspot and hot moment in the across the landscape. So from both aspects, the modeling approach can provide initial knowledge to guide where we should deploy more sensor and what variable we should pay attention to.
Thank you. We have a lot more questions, but we're running out of time. So Zenon, feel free to answer the questions on Slido.
Yep.
And with that, I will turn it over to Urindam.
Yep, thanks.
Thanks, Ime. So I'm actually excited to introduce our colleague, Professor Anima Anand-Kumar, as our keynote speaker for the workshop. Thanks, Anima, for joining. Anima is currently a Bren Professor at Caltech, where she co-leads the AI for Science initiative, among other leadership roles. She's also a Director of Machine Learning Research at NVIDIA, so she's wearing multiple hats. And she has made several core technical contributions in machine learning and AI, and particularly has spearheaded the development of tensor algorithms, which is now getting used everywhere in AI applications. Please join me in welcoming Anima as the keynote speaker.
Hi, everyone. Great to be here, and apologies for the earlier mix-up. It's always a bit challenging when it's early, and thank you for understanding, and thank you for being here, and thank you, Arindam, for organizing this. So yeah, let me share the screen. Give me 1 second. I think yeah, just give me 1 second. It should work. Yeah. Did you see, or?
We are seeing your Slack.
Oh, why did it go to Slack? I think I pressed I thought I did I did yeah, this is better. Sorry about that. Great. So I want to, give an overview of our recent work on learning neural operators for solving PDEs, and more generally, right, how to capture complex phenomena we see that are highly multi-scale and possibly chaotic. So how do we handle these systems at scale? And it is no exaggeration that differential equations are considered one of the most powerful tools humanity has ever created, right? Everything from fluid flow to modeling material properties, looking at seismology, right? The activities of the earth. All these require highly multi-scale phenomena that can be captured by partial differential equations. So what makes it challenging for traditional methods to solve is the inability to generalize, right? So, it's doing brute force numerical calculations and doing it also at multiple scales. You can't solve this complex problem all at once. You have to do finer scale calculations and be able to exchange that with coarser scale calculations. And this constant exchange is very expensive and requires supercomputers for some of the most challenging cases. And so the question is, can we use the power of machine learning to speed this up? And how we can possibly speed this up is to think about generalization, right? So if you've already solved problems, let's say with some set of initial conditions or boundary conditions for a family of fluid flows, there should be similar related solutions for similar or at least, in a way related solutions for others in the same family, right? So there is certainly what we know is ultimately the solution operator, right? So this is the represents the solution for any finite dimensional discretization of your inputs, right? If you can learn that efficiently, then you can solve this any equation in this family effectively. And so the question is, how do we learn that well? And so that's why we call it neural operator learning. Can we learn this solution operator in a tractable way and with guarantees? And this is an interdisciplinary work, having people from applied math, material sciences, and that's what kind of informs us in terms of what traditional methods are doing and how we can obtain, right, inspiration from that to design tractable and guaranteed AI methods. Yeah, so the way we want to set this up is the input can be a set of coefficients, which are initial conditions and boundary conditions, right? And from that, you want to be able to predict the solution. And so the main difference from many other works that look at learning on PDEs is that those works focus on learning one instance of the problem. So meaning you're kind of given one fixed initial and boundary condition, you want to learn the solution. But the problem is, this is only useful if you're using just that exact setting many, many times, right? Then the neural network can have a good speed up. But on the other hand, if you need to be able to change the conditions and try this on a new one, you would have to retrain the model. So that's not very effective. So what we instead need is one that can directly be able to give you the solution for any initial or boundary condition. And so the main aspect that I mentioned that is different from traditional neural networks is this ability to have infinite dimensional mappings, right? So, or continuous mappings. So for standard neural networks, the inputs and outputs are finite dimensional. Could be image, could be text, right? So, the text could be variable length, but still the vocabulary is fixed and finite. On the other hand, if you think about solving partial differential equations, right, ultimately you would need the solution at any arbitrary resolution, right, any arbitrary point in the domain, and the domains themselves could be arbitrarily shaped. So how do we learn this mapping between potentially infinite dimensional spaces? And that's what is an operator, right? It maps function to function. So that aspect, how do we incorporate that in learning neural networks? So I think the way we do this as building blocks is similar to how we think of the standard neural networks. In a standard neural network, you have some fixed dimensional input and you want to output against, right, in some fixed dimension. Let's say in the classification problem, it's some label that you want to output. And what you have is some linear function and composing it with nonlinearity. And what we want to extend this to is infinite dimensional mapping. So where the input would be some infinite dimensional function, and the output could also be potentially infinite dimensional. So how do we capture that and still get a universal approximator for learning operators? And that's what we call the neural operator. And the main building block here for the linear layer is what we call the integral operator. And so the inspiration of this comes from solving linear PDEs, right? So if it's a linear PDEs, we already know the structure of it is in the form of integration with the Green's function or a kernel. So this kernel represents the Green's function, and this is a continuous convolution operation. And through that, you can obtain solution for equations such as, say, the heat diffusion equations. So we know the structure of the equations in those settings. And so now the way we want to formulate it is to start with that integral operator, compose it with nonlinearity. And by doing that, we can now capture any nonlinear PDEs, right? So that's the outcome in terms of getting inspiration on how to solve linear PDEs and using that as a building block by composing it with nonlinearity together to come up with universal approximation for any operator. So now, theoretically, you should be able to solve any nonlinear PDE and learn that using this neural operator framework. So that's the foundation, right? So we've now been able to extend the notion of universal approximation for finite dimensional neural networks to ones that are potentially in infinite dimensions, and still be able to have the notion of linear operator here, right? So this is now integration over a continuous domain, but this is continuous integration, right? But by composing it with nonlinearity, we can get any general approximation. So this is a general framework, and indeed we can prove that similar to the counterpart, what we have with finite dimensional neural networks, that it can universally approximate any continuous operator. And so now for, in fact, for very well-known families of equations, say like the Navier-Stokes, right? So that is for fluid flow. We know that the solution operator lives in finite dimension, right? So even though it's mapping between infinite dimensional spaces, the solution operator itself is of low dimension. And so given that information, we would expect also the neural operator to have a small number of parameters. And that's how you can prove that the number of parameters of such a neural network would not be too high. So this is giving now some finite approximation bounds when the solution operator is also of finite dimension. And so that's the main aspect here, right? There is no magic. If everything was infinite dimensional, there is no way we could get a good approximation using only finite dimensional neural networks of finite size. Instead, what we have is solution operators that in many of these popular families are finite dimensional or low dimensional. Hence, we can expect efficient learning here. And that's the overall framework that, as a conceptual one, what we want to build are nonlinear compositions of integral operators, or these operators, right, that look at integration with the kernel. And if we can learn what this kernel integration is, then we can, compose it with nonlinearity and get a solution in the end. So now the question is, how do we still solve this efficiently, right? This is now a continuous operator, right? So this is also hard to solve if you are only given finite inputs. So you're given inputs of different discretizations, or even different samples, say even of the same discretization. You have to go from those discretizations to this continuous domain. So how do you do that? How do you get a good approximation of this kernel integration? And that's where we tried several variations. Natural aspect is to think about graphs, right, to do this kernel integration, because you can think of nearest neighbor kind of graphs that look at discretizations, discrete approximations of this continuous integral. But the one that worked really well in our setting is called the Fourier neural operator, where we use the Fourier transform to solve this convolution efficiently. So if you remember, so that's kind of the, the first I wanted to bring this up. If you remember, your signal processing 101, right, the convolution in the standard domain becomes multiplication in the Fourier domain, right? So if you assume this kernel is translation invariant, which is a reasonable assumption to make in many of these situations, right? So what we would get is this convolution is nothing but a multiplication, element-wise multiplication in the Fourier domain. And so learning this kernel for convolution is equivalent to learning a weighting matrix for the Fourier transform of your input. And so with this in mind, what we think of now, this convolution operator is one that takes the Fourier transform of your input and then filters in the Fourier domain and does the inverse Fourier transform. So what we also add in addition is an inductive bias where we pick only the low frequency mode of this, of the input Fourier transform. And the intuition is by picking the low frequency modes, we can invert it in a stable way. And because of nonlinearity, you can still get overall in the end, the high frequency modes, right? You don't have to solve for that in one layer of this network. And so that's a good regularization to enable learning well. And the reason we pick Fourier transform is what we want is to be able to capture global correlations. Whereas if you only have your standard convolutional neural network, it captures only local information, right? So, like edges. But in fluid flow, there is highly global correlation, both in space and time, right? So like currents here would have an impact all the way over here and all the way forward in time. So you cannot just use small window convolutions to be able to capture that. So that's the reason standard networks like UNets do not usually work well if you are trying to learn this from scratch. If you have to solve for this from scratch, they won't be able to capture this global phenomenon very well. And so what we see is this is the first machine learning method to be able to solve Navier-Stokes very efficiently and be 1,000 times faster compared to traditional methods. And also the benefit of having this resolution-free training is that you can afford to train just on low resolution and directly get this zero-shot super resolution. So the idea is we can capture this, rich information through operator learning. And indeed, the training resolution cannot be arbitrarily small, right? So you need at least some minimum level of resolution to capture the underlying solution operator. But once you capture that, you don't need higher resolution training data. And that's kind of what makes this work very well. And so you also have cheap training. You don't have to get expensive training data. And so that's the benefit of this method. And we also compared it with other machine learning methods, which only work on the same resolution. They cannot generalize to higher resolutions beyond. And so that's, and even there we see our method getting to a much better error, right? So the idea is by being able to generalize to other resolutions, you also learn well to generalize in the same resolution. And be also able to capture the higher frequency spectrum. So what we see is, again, if you use the Sobolev norm, the H2 norm, you're also fitting to derivatives up to second order, and that captures the spectrum much more effectively compared to just the L2 norm. And these are much more effective compared to UNet and other standard neural networks. And so that's the idea, being able to capture also this high frequencies, and that's how you can be able to resolve these higher resolution inputs. So with this, we can solve inverse problems very well, because what they require is a lot of forward evaluations. And so we can get a good speed up there. Many other applications of this, we've had the plasticity, which requires multi-scale, simulations. And there the speed up is even higher, because the standard packages are on CPU, and there's a lot of room you also get by moving on to GPUs and with neural networks. So you get the double benefits together here. And in ultrasound simulation, what we need is the ability to simulate how it travels through the body and the organs, and be able to capture both the wavefront and diffraction very well here. Like carbon dioxide, being able to handle that is a pressing problem of our times, right? So being able to model the gas saturation and pressure over the next 30 years is so critical. And what we've seen is very promising results in this regard. And so the other aspect is to also be able to capture both the physical constraints along with data-driven methods, the physical constraints being the equation laws itself, right? So can we fit to this equation laws? And what we see is this ability to, if you're training a PIN model, that is, you're using only the equation constraint and no data and no pre-training, it is, especially in the challenging regime of trying to predict for a longer time interval, we see that training from scratch doesn't get to the same error as being able to, first have the pre-trained model over the set of equations, set of data, and be able to fine-tune on a given test instance. And we see that as well, being able to generalize, from one Reynolds number to another, being able to do that in the turbulent regime well. So I don't want to go into this more, because I want to leave a few minutes for questions. But the idea is we can also capture invariant statistics, say in chaotic systems where you cannot hope to predict long-term behavior, but what we show is being able to capture the invariant statistics well. Yeah, so to conclude here, what we showed is the neural operator being able to frame this as learning the solution operator itself. So there is no dependence on a resolution or grid. And the Fourier basis helps us solve this continuous integration and approximate it in a good way, in an efficient way. And so being able to compose that over several layers gives us the ability to approximate any nonlinear PDEs and be able to generalize very efficiently. Thank you.
Thanks, Anima. This was great talk. We have quite a few questions. Before we get to the questions, quick announcement. So poster session starts at 12:30 Central Time. This is going to be on ML and climate. So keep that in mind. So let's get to the questions. Maybe we have time for a couple of questions. So one question is, somebody wrote that I'm very confused about how the convolution, which is linear, that is first power of V, can be applied to nonlinear problem. Can you clarify?
Yeah, that was the whole aspect here, that it is composed with nonlinearities like ReLU or something else. So yes, each layer is linear, but overall it's composed with nonlinearity. So that's why it can be a general universal approximator. Same as in a finite neural network, right? So you have matrix multiplication, which is linear, and you compose that with ReLU or some nonlinearity.
Okay. Another question is, do you implement convolution operation in Fourier transform form? If so, what are the benefits of it? Can we use similar idea in computer vision domain?
Yeah, so the main benefit is the ability to capture more global correlations. which is very crucial for these applications. And we know that the aspect of learning the solution operator well is being able to capture the frequency spectrum well, right? So if by operating in the Fourier domain, we can step by step do that. I mean, we don't claim in one layer you can't capture the whole Fourier spectrum because we are filtering to just low frequency modes. But by using nonlinearity and composing it over several layers, we can get a good approximation.
Okay, so we are getting a lot of questions in Slido, so maybe we have time for one more. So the FNO is elegant. Can it be used to learn randomly located forcing terms? That is, learn a PD that works for any emission sources without retraining.
Yeah, I mean, so this is a purely data-driven method, right? We don't even need to assume the equation structure in any way. So it can capture any kind of complex phenomena, especially those that are not limited to one grid or one resolution or highly multi-scale. Those would be great use cases.
Okay, so I think we'll wrap up, but Anima, if you can, I have a quick question, if you can quickly answer. So Fourier is one of the folks' favorites, orthonormal basis that we transform things to, but there was a phase in ML and signal processing where people were looking at dictionary learning, where even that basis was being learned from the data. I don't know if you guys have looked at that or considered that, or Fourier does seem like something fundamentally better.
Yeah, I mean, the main challenge is to be able to learn something global, right? So the convolution neural network learns it locally small once, and it's too many parameters if you try to learn it globally. And so that's why the Fourier is a good inductive bias.
Makes sense. Thanks so much. Thanks, Anima, for the talk, and thanks everybody for joining. We'll take a couple of minutes break, and then the poster session will get started. Thanks, everybody.
Thank you so much. Bye.